Now that we've hopefully gotten a relatively reasonable handle on converting between lists of numbers and then formulas for them, I want to go back to that calculus idea of figuring out the limits of sequences. And so a lot of the time it'll just be convenient to draw a picture and just sort of think about what's happening for each of these sequences. And so in this example, let's go through the first three sequences that we talked about originally. And so if I'm looking at the sequence of 1 over 2 to the n, then again I might start by drawing this where I have an n axis and an a sub n axis. And I'm just going to plug in different values of n here. And so it's going to start at 1/2, and then it might move down to 1/4, and then 1/8, and so on, and just cutting in half each time. And then if I sort of keep on drawing the dots like this, it's probably not too hard to imagine that overall this sequence is tending towards 0. And so the limit as n goes to infinity of a sub n is going to be equal to 0 for this. And so in this case, we would say that the sequence converges to 0. All right, so now let's look at the next sequence, which is 2n plus 1. And so maybe this is slightly different than the one we did on the last page where it was 2n minus 1, but the idea is still the same. Again, we can draw a picture of what's going on here. And so I want an n axis again and an a sub n axis. And I can see that when I plug in n equals 1 into this formula, then I'm going to end up with 3. And so maybe I'll actually let these go up by 2's here on this axis, just so I have more room. And so when I plug in n equals 1, then I'm going to get a 3. And then when I plug in n equals 2, I'm going to get 5. And then when I plug in n equals 3, I'm going to get 7, and so on. And so 4, that'll be a 9. And then if I had drawn this a little bit better, then this would have formed a straight line going up here with a slope of 2, of course. This isn't really any different from drawing the line y equals 2x plus 1. And so you can see in this case that the limit as n goes to infinity of a sub n, that's equal to positive infinity. And so in this case, we would say that the sequence diverges to infinity. All right, let's look at the next example. So here, if we have an is equal to minus 1 to the n, then when I sketch a graph of this, then again I'll have my n axis and my a sub n axis, and here I'm going to have a plus 1 and a minus 1 on this axis, and then maybe 1, 2, 3, 4, 5, and so on. And so when I plug in 1 into this formula, I get a negative 1. When I plug in 2, I get a 1. When I plug in 3, I get a minus 1. And it just bounces back and forth between these two over and over and over again forever. And so here you can see that these dots aren't really getting closer together, and they're not approaching a number overall because it keeps on bouncing back and forth between the upper dots and the lower dots. And so this sequence, a sub n, diverges. And so we can't say it diverges to anything because the dots just aren't approaching anything. And so this really diverges, and this is because it oscillates. All right, and so the last one we're going to look at is a little bit more complicated. And so here, if I want to look at the limit as n goes to infinity of n minus 4 over 2n plus 3, then now I have to figure out some way of determining what happens between the numerator and the denominator. And in this case, you can see that both the numerator and the denominator are approaching infinity. And so you absolutely could draw a graph of the sequence of numbers and try and analyze what's happening from there. But in this case, it's actually going to be easier to try and manipulate the formula directly. And so this is really similar to if we had a function of this form, so x minus 4 over 2x plus 3. And we might already have the guess that this 2n term is the biggest term in the denominator, and this n term up here is the biggest term in the numerator. And because those both have the same power of n, they're going to balance each other out. And so it's probably the coefficients in front of the n terms that's going to determine the limit overall. But in order to see that a little bit better, what I'm going to do is divide the numerator and the denominator by the leading term. And so by the leading term, what I mean is the biggest thing that appears either in the numerator or the denominator. It doesn't matter which way, just the biggest term that you can find. And so in this case, that would be an n. And so if I do that, if I sort of divide the numerator by n, then I'm going to get a 1 minus 4 over n. And then if I divide the denominator by n, I'm going to get a 2 plus 3 over n. And so the advantage of rewriting this is that this term individually definitely goes to 0. This term individually definitely goes to 0 as n goes to infinity. And the other terms just stay along for the ride. And so for that reason, this limit overall has to be 1/2. And so we've sort of made it more rigorous what our intuition was from before. And so we already knew that the leading terms of this sequence were probably what mattered, but we showed it more rigorously through this computation here. Okay, so one thing that's really related to this is that if this had been a function x minus 4 over 2x plus 3, then another approach to this would have been to use L'Hopital's. But this is a sequence of numbers, and so it's not a function because it's a list of dots, like the pictures that we've seen in the previous parts. And so maybe it's the case that we can't use L'Hopital's for sequences. Well, it turns out that there's a theorem that we can look at that will tell us exactly when it is still okay to use L'Hopital's rule for a sequence. And so this theorem looks a little bit abstract, but we'll talk about it through some examples, and hopefully it won't look as bad when we see the examples. And so the theorem says if we can find a continuous function, f of x, where f of n is equal to a sub n for all n, then the limit is going to work out between the function and the sequence. And so it says that if we take the limit of the function, it ends up giving us the same thing as the limit of the sequence. And this, again, is going to be a helpful trick because it will allow us to use L'Hopital's rule. All right, so I need to go back then and figure out what this might mean for this sequence right here. It's this n minus 4 over 2n plus 3. So I'm just going to copy this over onto the next page just so that we can look at this example right here again. All right, and so let me try and show what this theorem is doing graphically first, and then we'll look at what it does sort of in terms of computations. And so if I try and draw a picture of this sequence again, and this is going to be a really rough sketch because the details don't make too much of a difference, but we'll just see what it looks like. And so again, in one axis I'm going to have an n, and the other axis I'm going to have an a sub n. Now I'm just going to start plugging in values of n. And so if I do that here, then when I plug in n equals 1, I get something that's negative. And so it's a minus 3 over 5. And then if I plug in n equals 2, then I'm going to get a minus 2 over 7 or something, and this keeps on being negative until n equals 4, where it's equal to 0, and then at that point it starts being positive. And then at the end of the day, we already saw that this sequence is going to end up approaching the line 1/2, whatever it is. All right, and so in these blue dots right here, which I'm going to make a little bit bigger, I'm representing the sequence again. And so what this theorem is saying is if I can find a way of connecting these dots with a line, and if I know the formula for this line where it actually agrees for each one of these things, then the limit of this green line, which is now a function, f of x, is going to be the same as the limit of the sequence itself, because they both have to go to the same spot overall, right? The further you go to the right, the dots and the green line both have to go to the same place. And so that's all the theorem is saying overall, but in practice, all that means is that for this problem, I just have to replace all the n's with x's. And so now this function right here, x minus 4 over 2x plus 4, this is valid for all inputs x. And so, in other words, it's not a collection of dots anymore. It is that green line that I drew. Just by replacing the n with x and saying that x can be any real number instead of just being integers. And now if I want to compute the limit as x goes to infinity of f of x, so that'll just be x minus 4 over 2x plus 4 again. And now the numerator and the denominator here both go to infinity, and so I can use L'Hopital's rule and take the derivative of the top and the bottom. And so the derivative of the top is just a 1, the derivative of the bottom is just a 2. Now there's nothing left in terms of x's, and so I can just drop that and get a 1/2 overall. All right, so at this point, after I've said this, it might seem like there's no difference between sequences and limits of functions. And I want to make sure that it's clear that there is sort of a slight difference between these, and it's not always the case that you can just replace stuff with x's and then find what the limit is. And so an example of this is if we look back at this sequence, a sub n is equal to minus 1 to the n. And so in this problem, if we try to replace this with f of x is equal to minus 1 to the x, then you can see that there's going to be a problem with this, because what does minus 1 to the 1/2 even mean? And so in other words, when I just replaced it, the n with an x here, this wasn't a valid function. And so it's not the case that I can just use this theorem for every possible sequence, because some of the time, if you replace the n with the x, you don't get a valid sequence. Some of the time there might be a different way of rewriting this sequence so that it can be represented as a function, and then you would be able to use this theorem. And in this case, we actually could do that by rewriting things in terms of trig functions. But the point here is just that you can't always blindly replace the n's with x's. Sometimes it's more complicated than that. Okay, now I'll ask you to try a couple problems about taking limits of sequences.